Students.
Good morning, sir.
Morning. Good morning. Yeah. Thank you. Okay. Okay. So any questions regarding this memory hierarchy, whatever we discussed so far? Let me share the screen. So is this screen visible? Hello?
Yes, sir.
Yeah, right. So so just we are continuing the lecture where we stopped in the last class. Okay, so in the last class we are discussing about various issues related to the cache. It's basically the mapping between the main memory and a cache. Okay, and we know that the cache is a bit small in size and very fast in access by CPU. So therefore, the CPU tries to access the cache first for any of its memory accesses and all. And if it's not there in cache, then the memory which is below its in the hierarchy, it's a main memory, so it will be access the main memory and then fetch the desired contents, and that's the way the CPU access the CPU fetch the instructions or data from the memory and all. So in that process, we have seen that the memory, based on its organization, and here we have seen the three broad architectures or organization of a memory. So one was the conventional one where the memory was organized in the form of words, sequence, words, organized as a stack of words in sequence. So therefore, the width of a memory will be one word. It's a 32 bits, and they are like kind of indexed, addressed, right? And the cache is also with having the same width. And then to transfer data between the cache and memory, you have a bus having the same width of 32 bits. So this is one way of memory organization. And with this, what happens, you can able to access a row in one access time, right? And afterwards, you can able to transfer the data to a cache or from cache to the memory using like in one cycle over a bus, through bus. Because the bus width equals to 32 bits. So therefore, it can able to transfer in each time or in every cycle, every bus cycle, it can able to transfer only 32 bits, right? And then with that, the problem is that suppose if the block size is larger in size, right, then it requires, because the block contains the multiple words. So therefore, for accessing here in this organization of this memory, for accessing every memory, every word, you need a specific access time is required, right? So therefore, suppose if a block contains 4 words, for example, and for accessing the 4 words, you require that 4 times the access time is required. And as well for transferring the data also, you require the 4 times the transfer data, the transferring the each word. For each word, whatever the transfer time is required, you require the 4 times of that, right? So that you can see in the like you can see here. For example, if the DRAM access time equals to 15 bus cycles, right? And the address because first of all the cache has to specify that actually which block it has to be fetched and all. So therefore that address will be passed on to the main memory in one cycle from the cache, and afterwards then you need to access the DRAM and fetch the words, and then you have to pass on the words to to the cache. So for transferring the data, it requires one cycle for per word. So therefore, if you have a 4 words, if you want to transfer a block where the block contains 4 words, in case of the memory organization that was shown in the first one, where it requires for address for receiving the address anyway 1 cycle. And since there are 4 words in a block, so therefore for accessing those 4 words and preparing the data, you require 4 times the access time, so 4 into 15 bus cycles. And then afterwards, once the data is ready, then for transferring the data through a bus, it requires again a 4 cycles, because for transferring one data transfer, that is 1 word, it requires 1 cycle. So therefore 4 cycles, total 65 cycles are required for transferring one block. So therefore, if you try to compute in terms of bytes per cycle, it is like 0.25 bytes per cycle will be the effective bandwidth or effective data transmission over this particular memory organization, right? And the other one is that, suppose here if you organize the memory and a cache such a way that it matches with the block. That means if a block equals to 4 words, suppose if you organize the memory is also as a width of 4 words, that means a row where one entry in a memory contains 4 words in a succession here, right, in a row. And similarly, if the cache is also organized in the same way, then, and if you make the bus width also equivalent to the equivalent to the width of a block or like size of the block, so in that case you can able to transfer the data or transfer a block of data in 17 cycles, because one for address receiving, and only one access time is required to fetch the entire 4 words, because the memory is organized like that. And then since the bus width equals to like 4 words, so therefore you can transfer the entire block in one cycle itself. So therefore 17 cycles are required. But this is very expensive, because organizing memory of these 4 words width and even maintaining the bus of 4 words. So this is the hardware complexity is more and expensive. So therefore, there is another way of organizing a memory in the form of memory banks, where each memory bank will be having a normal memory, having a memory with a width of 1 word only. But if you arrange these memories in a 4 successive, like in the form of a banks, it's nothing but actually there are 4 memory cords will be there. And here, if you arrange them in the form of a bank like this way, like a memory bank 0, 1, 2, 3, and so on. And here, one good thing over with this organization is that, so if the memory if the memory is organized in the form of banks, discrete banks, you can able to access the corresponding row of all banks together with one access time itself. That means suppose the first row of all these banks together can be accessed using one access time, using one access time itself, right? And with that, what happens for preparing the data, it will not take as the one which is like this structure, which is a memory organized with a word level ender. Because if it is organized in the banks and all, and they are interleaved, and here if you want to like fetch a block from this memory, and here the memory also is organized likewise. Here, for example, okay, word 1 is here, and the word 2 here, word 3 here, word 4 here, then the word 5, word 6, word 7, word 8. Likewise, if you can able to see that the first block will be nothing but the first row. The second block is nothing but second row. Likewise, the blocks are placed in this memory bank such a way that each row corresponds to one block kind of. So therefore, here in this memory bank, you can able to access the entire block in one access time itself. And then afterwards, since the bus width equals to narrow, so therefore, even though we access all the blocks together, but still the bus width equals to only 1 word. So therefore, since there are 4 words of a block, so it requires 4 cycles, because 1 word at a time it can able to transfer. So therefore, if you look at here, if the memory is organized in interleaved way, like the 4 bank interleaved memory, that means for fetching the data from the memory banks and then passing to the memory, passing to the cache and all, it requires about 1 plus 15 plus 4 into 1. That is 20 bus cycles are required. But this is almost close to the one whichever having the wider memory and wider cache and wider band bus and all. But here thing is that only the memory was organized in the form of a bank, and then the remaining cache and bus sizes will be remain same. So there are various ways because due to this, actually, even though if you have a block size of the block having the multiple words, you can able to transfer the data at a faster rate. compared to the conventional structure of a memory having only one only one structure, only single structure. Like you can say that here you can say the memory with a single bank, where here the memory here the data was organized in the form of words. So if you want to fetch a block, means you require that many number of times as a block, as the number of words contains in a block and all. Okay. Yeah, now, yeah, because all these things why we are discussing over here is that we know that actually we'll try to, when you're trying to access the cache, we'll try to make sure that most of the times whatever the CPU requires, it should be present in a cache memory and all. So for doing that, if you can increase the block size in a cache, right? So that it takes care about the spatial locality. So therefore the miss rate will come down. And again, if you increase the block size, the problem is that this one for transmission of a block, suppose there is a miss occurs at that time for transmission for fetching the block from a main memory to the cache and all, it requires a reasonable amount of time. That means the miss penalty will be the miss penalty whatever associated with for fetching the block from main memory to the cache and all. So that has to be taken care properly. Otherwise, no, even though the miss rate may be less, but as the miss penalty increases, so therefore CPU has to wait for quite a long time for getting the desired instruction or a data from a main memory and all. So in that context, we are discussing about these different types of memory and their miss penalties and all. So as you have seen here and all, if we have a memory of this type, the miss penalty is very large. And if you have these two types, the miss penalty is almost lowered by like 4 times if the block contains the 4 words. And there are advanced DRAM structures where it can able to try to reduce the miss penalty further. That we have seen here. One is that having this multiple memory banks put together, and with that you can able to access all memory banks together. So with that the access time will be reduced, and then the miss penalty will be reduced. That's what DRAM usually access for the entire row. And in case of burst mode means, it means if you want to blocks of larger sizes and all, then in that case we can able to fetch all the successive words in a reduced latency and all. It is nothing but if you can organize them in the form of memory banks and all. So the rows, the words in a particular row can be accessed in a single access time. So with that, the effective access time will be reduced, so that you can able to transfer that the miss penalty will come down. And not only that, and we have seen that the miss penalty is nothing but all these things together. Like for example, like getting the address and afterwards access time, and then the transfer time and all. So here it requires if it is like a interleaved memory, even though the access time will be reduced, access time will be same as the wider memory, but the transfer time will be more. Right, and again for that again there is advanced DRAMs and all. So they can able to transfer twice the rate in a one single clock cycle. Normally, in one cycle is required for transmission of one unit of the information, like one word or whatever. But here in the clock cycle, by using advanced RAMs and all, you can able to transfer the twice the rate, because the clock cycle you can see there are 2 edges will be there. Like one is the upgoing edge and other one is the downward edge. So you can able to make use of that, and you can able to transfer with the twice rate in a clock, where the rising and falling clock edges and all, you can able to transfer at double the speed. That's what it means. And yeah, this slide just to illustrate that, to give you a feel that actually, so how the DRAM has been evolved. That means the DRAM structures have been evolved. The RAMs have been evolved from last 30 years and all. You can able to see that in the early 80s and all, it is very expensive. It's not affordable for a common public and all. You can able to see at that time, for 1 gigabyte of DRAM, it costs about lakhs of dollars. Whereas now you can see that it's very much affordable so therefore even a normal PCs or even the handheld devices also, you have a RAM size of, you can see about 4 gigabytes and of RAM is available, right? And you can see that like the capacity versus the price. how it has been come down or made it, or it becomes very much economical, so that even the public can able to utilize that, make use of the higher size of RAMs. So with that, the applications, whatever, also has been expanded, right? Earlier and all, these computations are used only efforted by the organizations, defense or like government organizations, are very few of them used for scientific applications, because they are not at that time the systems are not affordable. So now as the systems have become cheaper and because of networking, connectivity, and all those things and all, now lots of the personal applications also added to these with these computers and all, right? And here this particular plot is nothing to just to like this is the DRAM, and for accessing a DRAM, for accessing a row of a DRAM, so you can able to see what is the access time, how it has been optimized or reduced over a period of time in 80s and all. For accessing a row in a DRAM, it's used to be the order of about 250 nanoseconds used to be there, 250 nanoseconds. And then over a period of 20-25 years, it has been reduced by 5 folds. It is like a 15, less than 15 nanoseconds for accessing a row, right? And then within a row, like the accessing a column within a row, you can have, this was the time, the blue curve, whatever it shows that accessing a column within a row. So this is the one. So this is also in the terms of nanoseconds and all. And first, if you identify the row, then from that row, you can able to identify, you can able to fetch the desired column if it is required. So for that, this red curve plot shows that the access time corresponds to a row, and whereas the blue curve corresponds to access time corresponds to a column and a column within a row. And then when you're then after knowing about or after discussing about the cache, how to access the cache and the relation between the mapping between the cache and the main memory, and we'll try to see that what is the impact of a cache on the overall performance, right? So and as we have already seen that the performance of a system is basically measured in terms of CPU time. That means when a program is executed, like how much time the CPU spends on that particular program to complete that process, to complete that program and all. So you can hear in this context, when you that means when the cache is coming to the picture, here the CPU time can be computed or can be assessed as the various components of CPU time. Here are, one is the program execution cycles. It means that when the CPU is executing instructions and all, like when it's executing instructions, because it will try to, for every instruction, it will fetch the instruction from a cache. If it is an instruction or if it is a data, it is fetched from the data memory and all. And if the desired instruction or data, if it is available in the corresponding cache, then the CPU will not waste any cycle at all. CPU, it means that if there is a desired data or instruction, if it is available in the cache, then the CPU, you will get a hit, so that the CPU will fetch the desired data or the instruction from the cache. So that is nothing but the hit time. That is in that process, we don't waste any CPU cycles. That means within a cycle itself, CPU can able to fetch the desired instruction or data. And the problem is that actually, if there is a miss, that means if the CPU fetches the instruction, want to fetch an instruction or want to fetch a data, and suppose if that instruction or data, if it is not available, if it is not in the cache, then we'll realize the miss. We'll realize the miss. So if there is a miss, then it means that the data is not available in the cache. So we had to bring the data from its lower hierarchy, that is from a main memory. And we aware that actually for accessing a main memory and all, the order of time, the number of cycles that are required to access the main memory will be much larger compared to cache. Whereas the cache you can able to handle or you can able to access within a cycle, whereas in case of main memory and all, it requires about close to like 50 to 100 cycles are required and all. So during that time, since the data is not available, you cannot execute that particular instruction or a particular program cannot go further. So therefore, what happens? The CPU stops the execution, like it stalls the instruction, and just wait for the data to be fetched from the main memory and all. So that is going to be memory stall cycles. It means that if the desired data is not available in memory, right? Available in memory means here available, not available in the cache. Then the CPU will wait for the data to be again fetched back and data make it available in the cache. So that particular time period for fetching the data from a main memory to the cache and make it available, and that is known to be a memory stall cycle. That means during that time the pipeline will be stopped and CPU will just waiting for that particular data to be available at this one. So these are known to be memory stall cycles and all. So the CPU time includes both the execution cycles and this memory stall cycles also. The memory stall cycles, and when we will get a memory stall cycles in case of misses, cache miss and all. In case of cache miss. So therefore, anyway, the execution cycles is nothing but for every instruction will try to access that, so it will be hit or like miss. In case of miss, we have to pay the penalty. That means the memory the pipeline has to be stalled, and then we have to fetch the data from the lower hierarchy. And the number of memory cycles can be computed like that. Like suppose the number of memory access per program multiplied by miss rate multiplied by miss penalty, right? And the memory access are nothing but for every instruction you need to access the memory, because all instructions will be there in the cache, in the either in the instruction cache, and if the data that is there in the data cache. So therefore, the memory access is nothing but the instructions per program. Instructions per program. So the memory access per program is nothing but instructions per program, and then the miss rate is nothing but misses per instruction. That means for every instruction, if it is a hit or miss, likewise, you can able to compute the miss rate as number of misses per the instruction, number of misses per instruction into miss penalty. Right? So this way you can able to compute the miss penalty. And just look at this numeric example, very simple. Suppose, for example, your system consists of two caches, instruction cache and data cache, and the miss rates are 2% and 4%, 2% and 4%. And whatever the miss, whether it may be the miss at the data or miss at the instruction cache and all. So the penalty is 100 cycles. Penalty is 100 cycles. That means to fetch the desired data from main memory to cache, it requires 100 cycles. And the basic CPI equals to 2. That means if the hit is there, it means that if the data is available in the cache and all, and when the CPU accesses that, it requires 2 cycles. It's a basic. That means the cycles per instruction, right? And then load and store instructions are 36% of the total instructions. Load and stores are out of the instructions, number of instructions in the memory, instructions in the program. Out of that, 36% corresponds to loads and stores, right? So why this is given is that actually here the data cache will be accessed only during the loads and stores only, right? And whereas instruction cache will be accessed for every instruction, for every all memory access first will go to the instruction cache, and if instruction is there, then it will be accessed. And then if that instruction happens to be the load and store, then that particular instruction will also access the data cache. At that time, if the data is not there, or if the particular cache entry was not there, then there is a miss at the data cache. So that's the reason that actually here it was mentioned. You can see loads and stores are 36% of the instructions. Then with these inputs, if you try to calculate, the instruction cache will generate it's like miss rate equals to 2%. So with that, the penalty offered by the instruction cache will be altogether will be 2%. So each miss will require a penalty of 100 cycles. So therefore, it's like 0.02 into 100 gives you 2 cycles. And the data cache will offer the miss penalty of, you can say 4%, but the data cache will receive this instructions only 36% of the total instructions. So therefore 0.36 into 0.04 into 100, that gives you about 1.44 cycles. So the actual CPI, or you can say that the overall CPI will be like hit time plus miss penalty. Here the miss penalty is due to these 2 caches and all. So the instruction cache will offer a miss penalty of 2 cycles, and the data cache will offer 1.44. Altogether will be 5.44. So here in this case, having these particular inputs like specifications, so the system will take an average of like 5.44 cycles for execution of one instruction, an average sense. So if it is ideal CPU, that means if the caches are, if you provide sufficient number of sufficient size of a cache and all. So in that case, assuming that if there is no misses at all, so in that case, in case of ideal situation, the CPU will be faster of this much time, 2.72 times faster compared to this particular practical scenario. So in the practice and all, due to the finite cache size and all, you have a miss rates will be there. And for these miss rates, the average CPI or the CPI that is required will be 5.44. And if there is no misses, then the CPU can execute at a rate of 2. So therefore, a fraction of this from 5.44 by 2 will provide you that how fast the CPU can able to perform in the ideal situation compared to the practical one. And here to achieve these goals and all, we'll try to see that we'll try to organize the cache. I will try to make the cache that such a way that the miss rates will be as less as possible, and not only miss rates and the miss penalties also, because the miss rate is there and then the miss rate involves with the miss penalty. And if you try to minimize the miss penalty, then obviously the performance can be improved. Yeah, then this is another just illustration that like average access time kind of a thing. For example, you can say that, yeah, as we know that the average memory access time depends on both hit rate, and the miss penalty also, because for execution of instructions, every time we need to access a memory, we need to access the instruction memory, and some of the cases where you need to access the data memory also, like data cache also. So here the overall access time of a memory will be, the overall access time depends upon, sometimes you'll get a miss, sometimes you'll get hit also, but most of the times hit, and very few occasions will get a miss. But the overall access time, hit time means within a cycle you can able to achieve, you can able to get back. In case of miss, you need to wait. That means the pipeline has to be stalled and you have to fetch the data, then you have to restart the instruction back. So therefore, average memory access time is nothing but combination of hit time plus the miss rate into miss penalty. So this is the example, simple example, like CPU with 1 nanosecond clock. If hit time equals to 1 cycle, it means that if the data or if the cache, if the entry is available, if the memory of the desired instruction or data is available in the memory, in the cycle itself, you can able to fetch that. You can able to use that by the CPU. If it is not there, then how much time it requires to fetch that and make use of that? It's nothing but miss penalty, 20 cycles, for example. And here the, like for example, the miss rate equals to 5%, that is given here. And with that, actually, if we try to compute as per this above expression, you can see that the 2 cycles is the average memory access time and all. 2 cycles is the average memory access time for with an access with a miss rate of 5% and all. If the suppose if you reduce the miss rate, then this access time will be reduced, right? If you reduce the miss rate instead of 5%, if you make it like somehow, if you make the cache or if you organize the cache with 2%, then it will be reduced. It is nothing but 1.4 nanoseconds itself. Right? Yeah, then this is the overall view of a performance summary in view of by introducing a cache between the CPU and a memory, between CPU and main memory. And suppose, for example, when you try to analyze the performance, suppose assume that the CPU performance is increased. That is nothing but that means CPU can able to access faster, can able to perform by using the CPU. That means the access time, not access, execution time of instruction, you can able to make it faster by using with some appropriate technology. If you make the CPU will be faster, for example, somehow, even still it depends on the overall execution time or overall performance, still depends upon the miss penalty, because it's not just the CPU. If you make it faster or if you make it efficient, it's not sufficient, because the CPU always it accesses the cache, it accesses the memory, because the entire program is in memory and that in turn will be placed in the cache and all. So therefore, it's not just if you optimize the CPU just for performing arithmetic or like logical operations and all. So that will improve definitely, but at the same time, because CPU highly depends on the memory access and all, so we had to see that the memory access time or overall that is also has to be optimized. So it means that even though if you increase the CPU performance, like CPU efficiency, but still it depends on the miss penalty. Like that is more significant because the overall, in an average sense, in the overall sense, the performance of a system depends on the CPU execution cycles. Plus, it also depends on the miss penalty also. So we'll try to see that how to minimize this miss penalty. So what are the other factors and all? Like decreasing the base CPI. It is nothing but depends upon the effectiveness of CPU and all. It's nothing but cycles per instruction. Cycles per instruction. So if you try to reduce the number of cycles, execution cycles per instruction, then the overall efficiency or the overall time for execution of a program that depends upon that mainly depends upon the memory stalls and all, because here we are reducing the number of cycles per instruction in the normal execution. And so if you see the overall efficiency or overall the performance and all, so in that case it heavily depends upon the memory stalls. It is because of the miss rate. And the other one is that actually you can able to increase the clock rate. You can able to increase the clock rate. Increasing the clock rate is nothing but reducing the clock cycle. It means that suppose we make a cache to be very effective, and with that earlier assuming that some older technologies, with that you can able to access the cache in 1 nanosecond. And suppose the good very high-end cache and efficient cache, where it can able to offer the access time of a cache will be like 1/4 of a nanosecond, for example. So in that case, actually, you can able to. It means that you can able to increase the clock rate. It means that the cycle width or cycle duration you are reducing. That means by using the efficient CPU and efficient cache, for example, cache access times, you can able to increase the clock rate, right? Increase the clock rate. That is nothing but clock cycle period can be reduced. Clock cycle period can be reduced, right? But what affects, even though if you can able to optimize those things, but still the overall performance depends upon the memory stall, because the memory stall is nothing but if the entry is not there in the cache, you have to fetch from the main memory. So it means that again the memory access time, whatever the components I have mentioned, you have to pass the address of the block, and then you need to access the like a particular row of a memory, and then you need to transfer the data and all. So that is not to be memory penalty. So even though if you can able to optimize the cache access time or like the CPU performance, all of them, but still it heavily depends upon the memory stalls. So in that case, even though if you increase the clock rate, then the memory stalls will also requires more CPU cycles and all, more CPU cycles. Unless if you make the access time of DRAM faster, the CPU requires, if you reduce the clock rate, means it requires more CPU cycles. So what I mean to say is that actually here, even though when you try to optimize the CPU performance, it inherently depends upon the performance of a cache, or the way the cache is organized, or the way the cache is accessed. So all these things will influence the overall performance of the system. So now, yeah, by knowing that, so far we discussed about only one organization of a cache is known to be direct mapped cache. So we have seen that how the direct mapped cache works and all, and how the mapping will be carried out, can be carried out between the main memory and a cache, that we have seen. And in that, actually, if you can able to organize the cache in a effective way, like with the direct mapped cache, we have seen that every memory location in the main memory is mapped to a particular entry in the cache, a particular entry in the cache, right? If there is some other entry there, it means that since the main memory is much larger compared to cache, so therefore there are multiple entries in the main memory will compete for a single location, will compete for a single unique location and all. So that way you have certain problems, like if you want to, if there is a miss and all, then if you want to fetch that one, definitely it has to be replaced some other entry, some other existing entry in the cache. And maybe that may be required immediately soon after if you replace that. So therefore it generates lots of misses and all. So one way to overcome that will be using the by using a fully associative cache. So in case of fully associative cache, as such, there is no restriction at all to place the contents of main memory into the cache and all. In case of direct mapped cache, it's a very stringent. Like every memory location in the main memory has a unique location in the cache, and with that, actually multiple entries are mapped to a single location. So there is a competition in that, and with that, the sometimes no the misses also will continuously arises. And the other extreme other approach will be very soft approach or very other extreme approach is fully associative. So here in the case of fully associative, there is no concept of direct mapping. Here it means that the cache entries, whatever, suppose the cache entry contains it's a capacity of 1,000 blocks. That means there are 1,000 entries in the cache and all. So these 1,000 entries in the cache are very flexible. It means that any memory location, main memory location can go anywhere into the cache and all, as long as the cache is empty, as long as some entries in the cache are available. So likewise, so here the case of fully associative means the fully associative cache means allows a given block to go anywhere in the cache entry. We'll see that what it is, right? So it means that there are 1,000 entries, and there may be like main memory may have like 1 million entries. These 1 million entries may compete for 1,000 entries, but there is no there is no such restriction as in the direct mapped memory, where we see that we have seen that using that block number modulo with the number of entries and all. So with that, the multiple entries, they have only one entry will be there. But here, even though there are 1 million entries, all these 1 million entries can compete yeah, equally for these 1,000 entries, whatever there in the cache. So with that, you can have certain advantage where the replacements will be easier as long as the cache entries are available and all. As long as in case of direct memory, direct mapped cache and all, it's not that way. Like when you are required a particular block to be placed into the cache and all, you have to see that if the cache, that particular cache entry, if it is free, you can able to place it without any replacement. Otherwise, you have to replace whatever the present block is there, that has to be replaced with the desired block and all. But here it's not that way. Like in case of fully associative, because it's so flexible and all, so all any block in the main memory can be placed in the anywhere in the cache. So that is one advantage with this fully associative cache. But the problem here is that in case of fully associative cache, since any block in the main memory can go in anywhere in the cache and all, so therefore when you are when you want to search the particular block in the cache and all, you have to search all entries and all. You have to search all entries. Whereas earlier, because of that restriction, the cache will maintain an index and all. So because based on that index, you can directly go to a particular location, cache location, and you can able to check it out with a tag, whether the block is the desired block or not, right? But here it's not the case. Here you have to check for all the entries. Like, so that means you need to have a comparator for every entry in the cache. It means that suppose if it is a fully associative cache of 1,000 entries in a cache, for example, in that case, you should have 1,000 comparators. You should have 1,000 comparators are required, and you need to compare all of them parallelly. And then in any of them, out of 1,000 comparators, if any of them gives you a success, it means that the corresponding block is present. Otherwise, it's not there. So here the expensive thing or like a complex thing is that as the cache size increases, in case of fully associative cache and all, so you require for every entry you require one comparator. So therefore, the number of comparators that are incorporated should be very high. So that is the problem with this fully associative cache. Let me request more access time. Then the other alternative will be here. These two are extremes: direct memory cache and fully associated. There are two extremes, right? And where direct memory cache is very restrictive or very stringent one, and whereas in case of fully associated cache, there is no restriction at all as such. And the other one is that it is in between that, known to be n-way set associative. So here in n-way set associative, the idea here is that suppose, for example, your cache size equals to, for example, 1,000 blocks. Your cache size equals to 1,000 blocks. In case of direct memory cache, you make that 1,000, if the cache size equals to 1,000 blocks, that means you made that cache as organized as 1,000 entries, where each entry corresponds to only one block, right? Whereas in case of fully associative, You have 1000 entries and the blocks can be anywhere at all. That means each entry contains only one block, but the blocks can be anywhere. Blocks can be placed anywhere in the cache. So therefore you have to check all of them. So that was the, whereas in case of set associative, n-way set associative, here here the way the cache is organized is that suppose the block cache contains 1000, cache can accommodate 1000 blocks means, and that depending upon the n number n-way associative, suppose for example you can divide the cache into, for example, 256 sets, 256 sets. Even though the cache can accommodate 1000 blocks, you are dividing the cache into 256 sets, right? Where each set can hold 4 blocks. Each set can hold 4 blocks. So therefore here you have some flexibility, some limited flexibility will be there. It means each set can hold 4 blocks. So therefore multiple blocks in the main memory can compete for a particular set, can compete for particular set. But here the set is not stringent. Set is not just only one block. Set can accommodate 4 blocks. So therefore the multiple entries that are competing for a specific set, where that in that set if there is empty space is there, then you can able to place the block. That means the blocks within a set can be placed in a flexible way. So with that, actually here, whereas in case of fully associative, there is no concept of sets or whatever. So all entries are available. That is nothing but a single set. That means all entries can be viewed as a single set. So therefore, that means the main memory block can be placed anywhere. Whereas in case of set associative, where the cache is organized in the form of sets, right? And then well, by using that expression here, you can see that the block number modulo set, modulo number of sets. So with that, what happens? The block number will be assigned to a particular set, Then we have to see that in that set, if there is any empty place is there or not. If there is empty place in that set, right, then the block can be safely placed there, right? And if the entire set is full, for example, direct memory cache, there is no that flexibility at all, because the set there, the concept of set means set contains only one block. So therefore, if you mapped a particular set that contains only one block, so you have to replace that entry with the required block and all. So that way, this set associative will provide you there is some like intermediate limited flexibility. So with that, you can able to manage or you can able to optimize the miss rate to some extent. But at the same time, since here this is set associative, the same thing like that depending upon the n, how many blocks the set can accommodate. So the number of comparisons here that need to be made, that depending upon the number of blocks that set can accommodate. So if it is n-way cache, it means that you require n comparators are required. N comparators are required for every set and all. Because you are directly go to the set by giving a block number, you can come to know that where this block is present, which set this block can be present, can be available. And then if you go to the set, if you go to that specific set, that set contains the multiple blocks. And then from that blocks, we need to find out whether the desired block is present or not, right? So for that purpose, within a set, you need to perform all the comparisons. That means if the set contains the 4 blocks, so you need to perform 4 comparisons you need to perform. So with that, you can come to know that whether the desired block is present or not, whether the desired block is present or not. If it is not there, then it's a miss. So it's like we can say that it's like intermediate way of between these two extremes, direct mapped and fully associated. We'll see these with example, then it will be clear to you. Here you can see that here the cache size equals to 8 blocks overall. The cache size equals to 8 blocks. In case of direct mapped cache and all, so the cache is organized in the form, you know that the data followed by tag and a valid bit will be there, right? And in case of direct mapped cache, we know that suppose try to recollect the example what we discussed earlier. So assuming that here the map cache size equals to 8 blocks, or where the block equals to 1 word, and whereas the main memory contains 32 words. So therefore here it means that the four words in the main memory compete for a single location. For example, this blue location, if we choose it, So this is computed by the four words in the main memory and all in the main memory. So for all those four words, this is the only one location where you have to place them if it is required. So therefore, in case of direct mapped cache and all, and based on the by performing the block number like modulo with the number of cache entries and all, you will directly come to a particular location where you can able to search the tag, and where you can able to compare the tag. With that, you will come to know that whether the block is present or not. So therefore, in case of direct mapped cache, the access time will be faster. You can directly come to a location and directly with one comparison, you will come to know that whether whether the required block is present or not. Whereas in case of set associative, here the same cache is organized in the form of four sets, set 0, 1, 2, 3, where each set can accommodate two blocks. So in this case, the same cache is organized into a set associative, where the number of sets equals to 4, and it's a two-way set associative. That means there are two blocks. The block can be placed either over here or here and all. So therefore, the same way, suppose for example, if you perform that given the block number, you can come to know that the block may present in set 0, for example. For example, the blue one, for example, this is your desired block. And when you perform that modulo with the set numbers and all, you can identify that your block may present in the set 0. And again, to check that whether the set 0 contains your desired block or not, you need to search or you need to compare both the entries, this one and this one. We need to compare this and this together, both of them. Like if none of them satisfies, if none of them tell you that actually the block is not the desired one, then it's a miss. So what I mean to say is that in case of set associative, you require the two comparisons. Whereas in case of direct map, you have only one comparison. Whereas here, you need to search for all entries within a set. So there are two entries here because it's a two-way set associative. So we need to compare twice, like two axes. Two comparisons you have to make. So and likewise, suppose for example, it's a four-way set associative, assuming that. So in that case, how many sets will be there? Two sets, right? If it is a four-way set associative, it means that a set can have the four blocks, four entries. So in that case, the number of sets will be here. This particular cache will be resulted into two sets, set 0, set 1, where set 0 contains four entries, set 1 contains another four entries. So here in this case, we need to compare 4 times, like for all 4 entries in the cache be compared, right? Okay, so that way the number of sets that as the number of associativity in the set increases, that means the number of comparisons will increase. And in case of fully associative, as I mentioned here, the block can be placed anywhere. It's nothing but you can view this as the entire cache consists of only one set. The entire cache can be viewed as only one set, where that set has like whatever the size of the cache, like suppose if it is a M block size, M block cache, then you can say that it's the M associative cache. And where the number of sets equals to 1, number of sets equals to 1. So here in this case, as I mentioned here, so it's a fully flexible. So we don't know where the block will be available. So therefore, we need to search for all the entries. You can see here. We need to compare with all tags, all the tags and all. So whichever the tags results you the match and all, then you can say that yeah, the desired block is present at this particular location and all. And if none of them matches, it means that it's a miss. Right? So if you look at the various associatives, how this cache will be organized, you can see this different. You can see the different diagrams. You can say that. You can say one is a very vertical one. This is nothing but a direct mapped cache and all. And where it can able to accommodate 8 blocks, and there are 8 entries will be there directly, right? And so you can view this as like you can say that if you want to view if you want to term this as with respect to set associative, you can say that the number of sets are 8, and this is one-way set associative. That means each set contains only one block, so it's a one-way set associative. There are 8 sets are there. And then the two-way set associative means here a set contains 2 entries. A set contains 2 blocks, right? So therefore here you can say in case of two-way set associative, you have 4 sets are there. And the corresponding here, this tag and data corresponds to the first block, tag and data corresponds to second block likewise. If it is a four-way set associative, we have only two sets will be there, right? Each set contains the four blocks, like tag data, you can see that there are four, right? And there are eight-way set associative or fully associative because there are only 8 entries in the 8 blocks can accommodate. So therefore, at the other extreme, fully associative, or can we say that 8-way set associative contains only one set and where it contains all the blocks. That means the block can be placed anywhere and all. So yeah, this is one way to look at how the cache is organized with respect to various associations. And this is an example just to show that for the previous cache structures, and if these are the block references 08, 06, 8 and all, and in that case, in case of direct mapped cache, how many misses will be result? In case of two-way set associative or fully set associative, how many blocks, how many misses can be resulted? And assuming that here the cache equals to can accommodate 4 blocks, maximum 4 blocks. So that way you can able to see that if it is a direct mapped cache for these references, it results all misses and all. And here that the color coding corresponds to red corresponds to replacing. That means already there is some entry in this particular entry and you are replacing that, right? And this dull colored one indicating that at that time it was a miss because of compulsory miss, because the cache entry is empty, because the valid bit is 0. Because of that you have a miss. So that is the, and this on the normal font like memory 0, it means that here the entry was there, the entry is there, and then it can accommodate there is like you are getting a new reference and that is accommodated in some other location, right? So these are here you can see that in direct mapped cache all 5 references will result into 5 misses. And in case of two-way set associative, you can see that you can have only 1 hit will be there and there are 4 misses. And if it is a fully associative, you can see that there are 3 misses and 2 hits are there. This is just a very simple naive illustration just to show that as you increase the associativity, the miss rate will be reduced. And this is just an same illustration with a particular data set like a spec 2000 and given the specification of a cache and this one, these are the miss rates that will be resultant and all. Like if you have a 64 kilobit cache, data cache, and then the block size equals to 16 words, and this is the data, this is a program, spec program, which involves like maybe kind of like a Hughes matrix multiplications or something like that. A program which involves a sequence of instructions, a huge number of instructions and all. And if you run this program on this scenario, then with different cache organizations, these are the miss rates and all. One way is nothing but direct mapped cache. It's a 10.3%. If you increase the associativity, the miss rate will be reduced. But as we know that if you increase the associativity, even though the miss rate come down, but there is another factor that was in the performance. There is access time and all. That's what, right? And this is an example just to illustrate that how the set associative cache works. You can see here by looking at here, this is here in this case, this is 4-way set associative. This is 4-way set associative. It means that here the set contains 4 blocks. 4-way set associative, right? It means that a set contains 4 blocks. Here the example is just same as the previous example what we have seen. We have 32-bit address. So earlier the cache size equals to 4 kilobytes. 4 kilobytes. So therefore 4 kilobytes means where a block contains there at that time 1 word. So therefore there are 4 kilobytes means 1K entries are there where each entry corresponds to 1 word. And directly you can map to that cache and then you can, that's a direct map to cache. We have seen that only one comparator is required and it checks the valid and tag bits together. And with that it results whether it's a hit or miss. And then the corresponding entry will be fetched from the cache, right? That is a direct map to cache. But here this is set associative. And this is 4-way set associative. 4-way set associative means each set carries 4 blocks. So therefore, to indicate the sets, number of sets here, how many bits are required? 8 bits. Because a set contains the 4 blocks, right? 4 blocks. So therefore, very earlier, actually, the block is indexed by 10 bits, right? Because each entry contains only one block. So that's the reason there are 10 bits used to be there. But here, the same cache, but we are organizing the cache in terms of set. So therefore, to realize the sets or to index the sets and all, to find out, given the block number, to find out which set the block contains, for that, you require these 8 bits. That 8 bits used to indicate a set index of the set, right? And for that, so index of the set, for that, given the block number, what we do, block number modulo with the number of sets. Number of that gives you that a block where it is present, which set the block may present and all. So here with that you can get the specific set index and all. So with that you can go to that particular index, and at that particular set, in that particular set, there are 4 blocks are available because it's a 4-way set associative. So among these 4 blocks, we have to check that which is there any one of the blocks contains the desired tag or not. So for that, here we are doing, you can see that you are comparing for every block. That means you require the 4 comparators and all. And the same thing, valid bit and corresponding tag will be checked, the same comparator circuit. And if any one of them matches, then it results 1. It results, one of them results 1. If the block is not available in this set, for example, then all will leads to 0. All these comparators output will be 0. And then if you sum up, if you add all the outputs, you will get a 0. That is nothing but miss. And if any one of them matches, then you will get a 1 output. You will get R output equals to 1 because one of them will be 1. So that you will get 1 output, right? So that way you can hit will be there. And now here there are 4 blocks are there. Out of these, we have to fetch the desired word, desired block, right? So for that, actually here, you take all these 4 outputs and pass on to the multiplexer. And the input to the multiplexer is nothing but the outcome of these comparators. Outcome of these comparators has to be given as another input of this multiplexer as a select lines, as a control lines. So using these outcome of this comparator, this multiplexer will select the desired block because the 4 blocks are given available in the set and all. Out of that, we need to find out which block is the desired block. That will be depends upon the comparator's output. So this comparator output is also fed as a control lines to this multiplexer. So with that, the multiplexer will select the one among these 4 blocks and all. One among these 4 blocks. So that way the desired block will be selected and all. And from that again, the desired word, if you want, again by using this word index, you can able to pick up the desired word and all if it is required. So that way you can able to fetch the the desired block from the set associative cache, and this is the overall architecture of a set associative cache, how it is implemented, what are the desired required different hardware components that involves and all. So this is the one. And yeah, I think now we can stop here because it's now time up. So mostly in the next class we'll try to complete this memory hierarchy. There is just another 2-3 slides regarding this cache details, and after that we'll go into the virtual memory. And again, there also we'll try to see the cache analogy between the secondary memory, or you can say that the disk versus the main memory and all. And again, in that case, the main memory acts as a cache and the disk acts as the secondary storage or actual data that is present over there. And again, the mapping between these two also kind of similar to the to some extent from main memory to the cache and all. Main memory to cache, because the main memory is not very large enough to hold the programs, right? Sometimes the program size may be beyond or maybe more than the main memory size, right? It obvious happens. So in that case, actually, we need to use the secondary memory. It's known to be disk, which is a much larger storage and all. So in that case, how do we map the data or the programs from a secondary memory to the primary memory or a main memory and all? So that is by using the concept of virtual memory. So the same analogy, almost like here the cache here we have dealt with the 2 memories, cache memory and main memory. And then in the next following class, we'll try to discuss with the main memory versus secondary memory or a disk. So in that case, how the mapping will be carried out. So that we'll discuss in the next class. With that, we can complete this memory hierarchy, and afterwards we'll move on to operating structures, operating systems. So let me stop here. Okay, I'm stopping the recording.